Hey everyone, it's your main math teacher, Mr. Boyd, and I'm super stoked today because, oh, shucks. You know, this always happens when I'm thinking about concavity, and I'm excited today because we're talking about extremes. Well, actually, extrema, actually, and intervals of increase and decrease, concavity, and inflection points. Cool, let's do it. All right, y'all, here's the deal. You already know about some of this stuff. You absolutely know what extrema are. You may have never heard of them, but we've been talking about them for quite a while now, especially with the derivative graphs. We call them max and min values. And all this is telling us, hey, extrema is the plural form of extreme. These are the most extreme values. Most extreme high value, most extreme lowest value. Intervals of increase and decrease, hey, we talked about those a little bit when we were doing derivative graphs. The deal is, all this stuff up here, where that comes from is from f prime. Okay, so that's what we're going to be looking at today. Concavity, that's new. I just had an experience with concavity just now. We'll talk about that more in a little bit. And inflection points. And something I'd like you to know before we get started, all this stuff is going to have to deal with second derivatives. Okay, that's the thing that people get really confused about when they're learning these concepts. And so I want you to have something in your notes that keeps these straight for you, because otherwise we can get really twisted up and our brain will get tied into a nice little delicious pretzel. So we don't really need that. All right, first of all, we talked about it before, but we need to talk about it again because this language is going to come up today. When we have some function, it has extrema. We didn't call them that before. We call them maxes and mins. Today I'm using extrema because that's less words than maxes and mins. So all it is, if it is the highest point in its local area, it's a local maximum. It's top of the hill. But if it's the very highest point on the whole entire graph, we call that the global. Global meaning we're including everything. That's the highest point anywhere. Same thing on the min. This is the global minimums. It's the lowest point anywhere on the graph, the lowest y value. And over here we have a local one. Ooh, little trick question. What is that point at the end right there? Is it max, min, global, local, or none of those? This one is a local max because it's the highest point in its local area, but it is not the highest point on the whole graph. Okay, let's continue. Let's look at an example. Okay, we are actually getting into test type questions right away here. Okay, so here's our first one. We want to find the global and local extrema, maxes and mins, of the function in this interval. Okay, so we've got our interval right here. First thing I want you to realize, that's very, very similar to what we just looked at. This one has some interval. It goes from here to there. It has two endpoints. So does the function we're about to look at. We're just going to do it algebraically. Okay, and if you think back, if we're finding maxes and mins, I need you to remember that comes from f prime. So the first thing I'm going to do is I'm going to take a derivative. Extrema come from f prime. Let's do a derivative. That would tell us that f prime equals, bring that down, 6x minus 12. Cool. And we want to find the critical points. Critical points, remember, that's where f prime equals 0. So that's what I'm going to do right here. I'm going to set this thing equal to 0. And that's going to tell us that x equals 2. Hey, good for us. That's great. We have to decide, though, is that a max or is that a min? It's absolutely a critical point, so it's one of the two. Here's how you can tell. There's a couple ways to tell, but my favorite is something called the first derivative test. And here's how it goes. We're going to put a number line down. We're going to put all of our points of interest. The only one we have right now is 2. And these are critical points. So, test of critical points. Okay, and I'm going to put 2 on there. There are 2 ways to do this. Some people call it a sign chart. We're trying to put pluses and minuses on these to understand where are we increasing or decreasing, or do we have positive slopes and negative slopes on the original function. And so what I'm looking at, I'm going to look first visually. I'm going to look at this. And the first question is, do you know what shape that is? Well, I hope you know it's a line. I hope you know it has a positive slope. It would look something like this. Okay, and so what we can do then is we can say, oh, over here it's above the axis, it's positive. Now remember, this is the derivative test. So this is the derivative. Positive means the original function was increasing. Over here it's below the axis, so it's negative. It means it was decreasing. Now maybe you're not a visual learner, and so this doesn't really work for you very well. So another way you could do this is you could either start picking numbers and plugging them in, or you could think of things that aren't numbers, that are concepts, and start plugging those in. So what I'm thinking about is, let's say I plugged in a number to the right over here. I could plug in 3. If I plugged in 3, that'd be 6 times 3, that's 18. 18 minus 12 is, I don't care because I know that it's a positive number, so I'm not actually going to calculate it, but it's positive. Or you could try infinity. 6 infinities, okay, that's big, pretty darn big, minus 12 is still a positive number. There you go. You can do the same thing the other direction. You could plug in a 0, because that's to the left of 2. Plug in a 0, 6 times 0 is 0, minus 12 is a negative number. Booyah, there you go. Or you could say negative infinity. If I plug in negative infinity, 6 times negative infinity is ridiculously big. Minus 12 more that way. That's still negative. Now, let's put this back in the context of what the heck we're trying to answer. We want the global and local extrema. So why were we doing this? We were trying to figure out if 2 is a max or a min. Here's how we do it. This negative right here says the function was decreasing. This plus right here said it then started increasing. If it was decreasing and then started increasing, right down there in the middle is a min. That's all it is. So that tells us right there we have a minimum value at x equals 2. Awesome. So we've got our critical points. The other thing we have to do, and we saw that in the visual, we have to test the endpoints. We need to know what happens there. So I'm going to come back down here and I'm going to test the endpoints. So right now what I know that x equals 2 was a minimum value. I need to test x equals 0 and I need to test x equals 3. So let's do that. Remember, I'm plugging them in. Wait a minute. Original or derivative? We're asked for the most extreme values of f. So I'm going to actually plug them into f. Okay, so I'm going right in here. Now, the 0 I can do in my head. 3 times 0 squared minus 12 times 0 plus 5, those all zero out, and 5 is what we have. So 0, 5 is a point on the graph. For the 3, I'm going to have to actually show the word. So 3 times 3 squared minus 12 times 3 plus 5. And so what do I have? Looks like I have 3 squared is 9 times 3 is 27 minus 36 plus 5. And correct me if I get this wrong, because I may. I think that's negative 4. Okay, and so I've got one combination here. I've got 3 comma negative 4. And so now we're going to start assigning some values to this. Okay, so here's the deal. I'm looking right here at the min. We have to decide if that's global or local. Take a look at what we've got. We've got a 5 there for our y value, a 4 there for our y value. Is this higher or lower than that? Well, I don't exactly know because we haven't tested it. So what I need a y value here. And what that will allow us to do is we can compare this y value to those y values and figure out if it's the very lowest y value. So I actually need to plug a 2 in for that. So let me change colors here. So I would get 3 times 2 squared minus 12 times 2 plus 5. Okay, let's run that out real quick. 2 squared is 4 times 3 is 12 minus 24 plus 5. Okay, I'm looking at negative 12 plus 5, that's negative 7. So now I've got negative 7, 5, and negative 4. What's the smallest number? Negative 7. So that was a global minimum. Okay, that's the first part of my answer. I found a global minimum. Where is my global max at? Looks like it's right here. That's the highest point on the whole thing. So that is my global max. And then this one, how do you tell if it's a max or a min? That's a little bit tricky because, I mean, you say, well, but it's negative, it's a min. Not necessarily. It doesn't have to be. It could be something like this, where we have a negative number, but it was a global min. And one thing I want you to notice, one way we could tell this was a min is because the function was lower before and it was increasing until it got there, which means the derivative was positive. We can do that same test for our question. So what I'm going to do to test that, I'm going to take the derivative, 6x minus 12, and I'm going to find f prime of 3, which would be 6 times 3 minus 12, which would be 6. Okay? And actually, I don't care that it's 6. All I care is it positive or negative? Because what that tells me is right up until this point, the function was increasing, and then boop, there's that point. Now you see I'm doing that? It's increasing. There's the point that was above all the points that were leading up to it, which means that this was a maximum value, actually. It is a local maximum because there is a value on the function that's higher. So let's double check the question and see if we answered it. It asked for all global and local extrema. We did that. They're right here. You've got a global min, which occurs at x equals 2, a global max, which occurs at x equals 0, and you have a local max that occurs at x equals 3. That's done. Okay, let's do another one. Okay, here we're being asked to find intervals of increase and decrease. Now remember, increasing and decreasing is a first derivative thing, so let's find our first derivative. Okay, there's my first derivative. And if I'm going to find my intervals, I need to find the zeros. Remember, those are called the critical points on the first derivative. So let's factor this out. So I get 3x times x minus 2. So my zeros of that are 0 and 2. And we're going to do the first derivative test. So we're going to have a 0 and we're going to have a 2. Now remember, we can do this visually or analytically. The visual way to do it is to ask ourselves, well, what does that function look like? 3x squared minus 6x, that's a parabola. It opens up. And so I could just go like this. And then I say, oh, okay, well that's above the axis, plus. That's below the axis, minus. That's above the axis, plus. And now I've got my sign chart. So when I have to write out the intervals of increase and decrease, it's pretty easy. It is increasing over the interval. Let's see. Well, it's increasing over here. So from negative infinity all the way up until 0. Or it's also increasing out here. So from 2 on to infinity. Where is it decreasing? Well, where we have a negative, from 0 to 2. Now we're done. That's it. Okay, now about concavity and inflection points. So right at the beginning, I was super stoked. I was drinking my water, and when I started, my cup was concave up, is what we call it. It holds water. Something like a parabola would be concave up. A boat that's floating in the water would be concave up. And everything was fine. It was holding water. Life was good until I tilted the cup and it was concave down and the water went flying. Okay, so concave down is going to look like this. Concave up is going to be upward. Okay. Where that happens at is inflection points. And we've talked about inflection points. We've just never used the language. When we graphed the derivatives, I called it the steepest point. Okay, and so I've got that label right here. We call it the steepest point. We made that the most extreme value on our derivative. You absolutely must know that where these occur is where f double prime equals 0. Okay, so we're switching gears here. We're talking about second derivatives now. Okay, so it's where your second derivative is 0 and there's a change in concavity where it goes from concave up to concave down or concave down to concave up. Okay, we do have some analogies for it. So we had whether or not the cup holds water. If the boat is floating right side up, that's concave up. If the boat flips, now it's concave down, not so good. The other one that I really like, especially this will make sense if you've driven a car before, is when you go around a corner. So if you're driving and you turn around a corner and then it has like a double S-curve like that. Right here, you started turning your wheels left, and then to get it out of it, you turn your wheels right. But at one point in time, at one moment, between here and there is one moment where your wheels, just for a moment, are pointing straight, right in here somewhere. So turning left, straighten out, turning right. That right there is an inflection point where you have downward concavity. If you look upward concavity, like if I continue this, see how it looks like a cup? This part down here, if I continued it, you can see it's concave down, or it has negative concavity. Okay? And the other thing I want you to know is that we are going to be asked to determine where these are concave up and concave down. And all we're looking at is the second derivative. Is it positive or is it negative? The same way just a minute ago, we looked at the first derivative to see if our function was increasing or decreasing. Second derivative will tell us about concavity. And so let's take a look at that. We're going to take the exact same function we had. We already know that f prime equals 3x squared minus 6x. This asks about concavity. When you see the word concavity, boom, that's a second derivative. Let's take a second derivative. F double prime is going to be 6x minus 6. Okay, and so the first thing we want to do is probably find our inflection points. Now recall from a minute ago, that's where f double prime equals 0. We have f double prime. Let's set it equal to 0. What number makes that true? That would be x equals 1. So that's our inflection point, and we've already answered that. Now previously, we used the first derivative test. You want to guess what we're going to use on this one? Second derivative test. Let's do it. Okay, so I'm going to plot down my inflection point, put a little 1, second derivative test. Alright, y'all. So it works just the way the first derivative test works, except this one finds concavity. Okay, so what we're going to do is we could do this one of two ways. We can look at our second derivative and ask ourselves, what does that look like? It's linear, has positive slope, So it's like this, which means plus, minus, above the axis, below the axis. Or, if you like plugging in numbers, how about we try a skillion? Let's plug in a skillion. 6 skillion minus 6 is definitely positive. There you go, it's over to the right. Plug in a number down there. How about negative a skillion? 6 times negative a skillion is a big negative number. Minus a number is even further down, so that's a negative. We're talking negative y values, okay? And so what that allows us to do is then write our concavity out. So I'm going to do concave up. Where does that happen? Where we see the plus sign. So that would go from 1 on to infinity. So concave up from 1 to infinity. And then we also need to say concave down. Where does that happen? Where I see the minus here on my second derivative test. That would be from negative infinity all the way up to 1. And so there we go. We've answered the question. Alright? We also want to be able to do this visually, make connections, and so we're going to identify the critical points and the inflection points on all of these graphs. Now some of this is review and some of it's new. I'm going to do my critical points in red. Let's do that first. So when we did the derivative graph lesson, lesson 2 from this unit, we noted that on an original function, critical points occurred at the maxes and mins, which we now know are called extrema. So right there and right there. And then what did they look like on our derivative graph? Well, there's 2 critical points here. There must be 2 critical points on the derivative. They occur right here and right there at the zeros. That's what a critical point is when f prime equals 0. What do they look like over here? Well, they don't look like much. I mean, they're just points. I think they're probably off the grid on this one. They're like way out there and way down here somewhere. So that's a reason why we don't use the second derivative to find critical points or intervals of increase and decrease. It starts to lose meaning as we keep taking derivatives. But let's talk about inflection points. I'm going to do inflection points in green. Okay, inflection points, now that's when the concavity changes. So notice right here, this is concave down, and then it switches, and now it's concave up. Well, somewhere between here and there must have been an inflection point, because that's where the concavity changes. And it looks to me like it's right in there. Now your eyes might see a little bit different, but you're also looking, remember, it's that steepest point that we talked about earlier. So it looks like it's right about there to me. Now, if that's the steepest, when we graph derivatives, that meant the most extreme y value on the derivative. And that's why our inflection point is right down here. And what does an inflection point look like on a second derivative? It's always a 0. Remember, inflection points are where f double prime equals 0. Okay? Alright, last one and we're done. Okay, this is a big test style question. We're going to do a bunch of stuff. We need critical points, inflection points, concave up, concave down, increasing, decreasing. This is going to culminate everything we've done today in one question. My suggestion to you is you pause the video and try this on your own, and then when you're ready, hit play. Okay, here we go. So, first thing I want to do is figure out which of these things go together. And I want to do first derivatives first because it's less steps. So, critical points, that's a first derivative thing. Inflection points, no. Concave up, concave down, no, that's not first derivative. Increasing, decreasing, that's first derivative. So let's do that first. So I'm going to find my first derivative. Let's see, bring that down. 9x squared minus 12x plus 2. Okay, that doesn't look too easy. And remember, critical points are where that's equal to 0. Now there's a chance that's factorable. It might factor. I think it's going to be easier if we use the quadratic formula. I think it's going to be less steps and less time. So I'm going to suggest we do it that way. So I'm going to start solving that. Remember, if you're trying to solve a quadratic, you want to consider factoring first, but if that doesn't work, you also need to consider quadratic formula, because that'll work every time. Okay, let's do this. Remember, it's negative b, so that would be 12, divided by 2a, that would be 18, plus or minus the square root of b squared, that's 144, minus 4ac. Okay, let's do some mental math here. 4 times a, so 4 times 9 is 36, times 2 is 72. Let's do a little bit of simplification now. So we've got this. I think that simplifies to 2/3. Oops. 2/3. And we have plus minus root 72 over 18. Okay, that's looking a little bit ugly, but here's what we can remember. 72 is the same thing as 36 times 2, which is the same thing as 6 times 6 times 2, which means we can simplify that radical. And so this actually will now say 2/3 plus or minus 6 root 2 over 3. And over 18. Sorry about that, I jumped ahead of myself here. And then 6 over 18 is 1/3. So simplifying this out all the way, I get 2 plus or minus root 2 over 3. And I'm going to label that, those are my critical points. Okay, we were asked for 4 things, one of them was critical points. That's down. Critical points are needed to find intervals of increase and decrease. So let's use our first derivative test and do that. And it's going to look a little ugly, but it's not bad. All we're going to do is we're going to put our critical points on there. Please realize that means there's 2 of them. Be careful with that. So over here I have the negative version. Negative means we're going to the left. So 2 minus root 2 over 3 and 2 plus root 2 over 3. And people get really freaked out and just go, oh, I don't know how big that is. No, it's not a big deal. Because all we're going to do is refer back to our derivative. That little guy is a quadratic. Does it open up or down? Looks like it opens up. And so I'm going to go ahead and toss my dotted line on there. And all I'm doing is I'm deciding if it's above the axis or below. That's above, put a plus. That's below, put a minus. That's above, put a plus. That tells us about increasing and decreasing. So maybe I should put first right here. So in case I look back at my work, I can remember that was a first derivative test for increasing and decreasing. That was the purpose of this. We want that to be clear in your notes. Okay, so now that I have that, I can actually write out my answer. It is increasing over the interval, I'm looking for the pluses, from negative infinity up until 2 minus root 2, root 2 over 3. And also from 2 plus root 2 over 3 to infinity. That's increasing. Let's talk about decreasing. Decreasing where there's a minus, it's in between these two. It's a lot of symbols, but it's not hard to write. So from 2 minus root 2 over 3 to 2 plus root 2 over 3 are my intervals of decrease. So sometimes what I like to do at this point in my work is kind of draw a line in the sand. And the reason I do that is everything we've done so far has been about first derivatives. And everything we're about to do is all about second derivatives. And if we mix our work together, that can get really, really confusing. So I like to separate them out, and so I can keep this straight. So now I'm switching, I'm doing second derivative stuff. And why am I doing that? Because I was asked for inflection points and concavity. Okay? So first thing I want to do, if I need a second derivative, I better take a derivative of the derivative. There it is, there's first derivative. I need a second derivative, so let's take another one. So what will that look like? It looks like the 2 will come down, and we'll get 18x. And then what? And then we'll get minus 12. Now you'll notice, when we start with a polynomial, this one was cubic, it gets easier as you take derivatives. It's less and less work. And so we need an inflection point. And that's where f double prime equals 0. And so now, all we have to do is set this equal to 0. Now y'all, I'm going to let you do mental math on this. This is going to come out to x equals 2/3. And that is an inflection point. And I'm going to circle that because that is part of what answers the question that was asked above. Once we have our inflection point, all we need is our second derivative test. Here we go. Remember, this is linear, positive slope. Or if you want, plug in big numbers. So if you want to do it visually, go ahead and plot that on there. Plus, minus. If you want to do it numerically, pop in a big number, like a million. 18 million minus 12. I don't know what that is, but I know it's positive. There you go, that matches. Plug in a big negative number. Let's do negative a million. So negative 18 million minus 12, that's negative 18 million 12, which is negative. That matches our chart. And so I'm going to do this. I'm going to abbreviate it this time. C plus for concave up. Concave up, over here, from negative infinity to 2/3. And concave down, let me get this out of the way, and it's concave down from 2/3 onward. There it is. We've answered the question. That's all for today. May your boats be concave up.